Welcome to our discussion on the real zeros of polynomials. Here are the topics that we're going to cover. Pretty standard stuff for finding uh, real, rational zeros of polynomials. Basically, we're going to find all zeros of polynomials except for complex zeros. We'll find complex zeros in other videos. All right, so we'll start off with just some theorems and some ideas, right? There's this factor theorem that tells us that finding zeros of a polynomial is really the exact same thing as just factoring it into linear terms. And you go, well, no, duh, because if I factored something into linear terms, I would know what all the zeros are. So we use that idea to help us find what we're going to call rational zeros of a polynomial. Remember, rational is just the type of number it is. It's just any number that can be represented by a fraction. And remember, whole numbers are fractions over 1, right? So we're basically just looking for kind of what we think of as normal solutions: 1, 2, -3, a half, 3.5, a third, things like that. All right, so how do we find these rational zeros of polynomials? Well, let's look at a simple example. If we started off with a polynomial factored, then we could look at that very plainly and go, all right, it's got a 0 at 2, 3, and -4, right? Now, if you multiply those out, if you FOIL all those things out, what we call the expanded form, or kind of like the standard form of the polynomial, is that second line, x cubed minus x squared minus 14x plus 24. And you'll see that the last number, 24, you get that from multiplying 2 times 3 times 4, right? I mean, technically you get it from, you know, because of the way it's set up, it's a -2 times a -3, and that cancels it out, right? Makes it positive, and then times the +4. So the zeros are, remember, always the opposite sign. So it'd be a +2, +3, and -4. And if we multiplied those together, we would get -24. But if you just kind of ignore the plus and minus, you can see that 24 comes from simply just multiplying our zeros, or you can think of it as like the absolute value of our zeros, right? But basically, this tells us that whenever we have a standard polynomial, and it has to be, with a leading coefficient of 1, then all of our zeros are going to just be factors of the constant term. Well, we can expand that and think, okay, well, what if the leading coefficient wasn't 1, right? What if the number in front of x cubed wasn't 1? Well, then we can generalize it. And we get this idea that what happens if we have that a sub n in the front, right? This leading term here that's not a 1. Well, then it's easy to prove, and it's easy to see that if we let p and q be whole numbers, right, integers, then every rational zero, every normal kind of number that makes our polynomial zero, i.e. the factors of it, are always going to be of the form p over q, where p is a factor of the constant term, that last number, and q is a factor of the leading coefficient. So you can see when the leading coefficient is 1, the only factor of 1 is 1, q becomes 1, and we get that all the zeros have to be factors of the constant term, which is what we just saw before. All right, so here's a simple example. Because our leading coefficient is 1, all of our zeros have to be factors of 2, so plus and minus 1, plus and minus 2. And now it's just a matter of testing each one. Plug in 1, see what happens. You get a 0. You go, yay, that one works, right? Plug in -1, doesn't work. Plug in 2, doesn't work. Plug in -2, and it works. And we see that the rational zeros of our polynomial are 1 and -2, which also now tells us 2 of the factors, right? If -2 is a 0, then x minus -2, which becomes x plus 2, is a factor. And because we saw originally that 1 also was 0, then x minus 1 is another factor. And then we can use that to find the third factor, right? Because it's x cubed, so we know there's 3 of them, because if we multiply this out, that'll just be x squared, right? So it'll help us find factors as well if we can find zeros. Okay, so here are the steps if we want to find the rational zeros of a polynomial and thus be able to find the factors, first we list out all of the possible zeros using the rational zeros theorem. That's the whole thing of the P over Q stuff, right? Once you have that, just start dividing. Use synthetic division if you know how to use it. That's the fastest way. If not, you can do long division. And you basically, unfortunately, it's just a trial and error. You'll start to see patterns that, like if you try 1 and it doesn't work, and you try 2 and the remainder gets worse, then you know the 0 is in the other direction. So instead of trying 3, go in the other direction and start trying the negatives, right? That kind of thing. And then you just repeat the process until you find all of them. So let's put this into an action and see how it works. Here's a typical polynomial. We list out all of our possible zeros, right? So we factor the constant term, factors of 6, and then factors the leading coefficient, which is 2. So it's going to be factors of 6 over factors of 2. We list those all out, right? Factors of 6 are plus and minus 1, 2, 3, and 6. Factors of 2, of course, are plus and minus 1 and 2. So you just basically take all of the factors of the constant term and just divide them one at a time by the factors of the first term. So you can see we took 1, 2, 3, and 6 and divided those all by 1. And then we took 1, 2, 3, and 6 and divided those all by 2. Of course, slap in plus and minuses in front of everything. And then you just get rid of doubles, right? Because 1 over 1 is the same thing as 2 over 2. And 6 over 2 is the same thing as 3 over 1. So when you get rid of doubles, you see that you really have a lot still to check. You've got plus and minus 1, 2, 3, 6, 1/2, and 3/2. Obviously start with the easy ones first. Try plus and minus 1, plus and minus 2, plus and minus 3, and kind of move out from there. So here's testing 1 with synthetic division. You get a remainder of -4, which doesn't work. Then you try 2. You get that remainder of 0, so that means 2 works. 2 is a 0. And also, if you remember from when we talked about synthetic division, this last row gives us the new polynomial, right? This means that we have a factor of x minus 2, and then this becomes the new resulting polynomial with x squared x, right? And I know this is square because, well, for one thing, there's 3 pieces, right? The last one has to be a constant, so it goes constant, and then x and x squared. And also because the original polynomial was a power of 3, and if we take a linear term out of it, we're down to a power of 2. And that's what we're talking about on this thing, right? That you can see that here is the same thing that I had from synthetic division. And then now that you have the second piece, right, is a quadratic, you can either factor or use the quadratic formula to find the other 2 zeros. And then there are your 3 zeros for your polynomial. Now that's pretty easy when it's a degree of 3. What happens when it's a 4, 5, 6, and so on and so forth? Well, basically you just keep doing the synthetic division until you get it down to a quadratic. And then once you have a quadratic, always stop. And at that point, factor it or use the quadratic formula. Right, so you basically use synthetic or long division to get it down to a quadratic, and then from there use our tools for quadratics. Now there are some things that will help us know kind of how many things we have to check, because it might not be that we don't have any. It could be that that was a horrible sentence. Let me try that again. It could be that we do not have any rational zeros, and so we don't want to keep spinning our wheels. So Descartes' rule of signs helps us kind of narrow the window down and know how many zeros that if we have them, there are. And it's very simple. If you start with your polynomial, right, and it's a normal polynomial that we're used to with real coefficients, which basically just means all the numbers in front of your powers of x have to be real normal numbers. They just can't be imaginary numbers, right? So they can be square roots, they can be, fractions, decimals, they just can't be imaginary. And now, if it's written in descending powers of x, and you omit powers with 0 coefficients, so you can see in this example, it went from power 7 to power 5. We didn't write a power 6 in there, like 0 times x to the 6. Then a variation in sign occurs whenever each adjacent pair changes. So we went from positive to negative, so that's a change in sign. We go from negative to negative, so nothing happens there. But then we went from positive Sorry, we went from negative here to positive, so that's another change in sign, right? So it's one change here, stays negative, changes again to positive, stays positive, changes again to negative. So you can see how we have three changes, three variations in signs. Now, what Descartes' rule tells us is that the number of positive real zeros of our polynomial is going to be equal to that number of variations, 3, or less than that number by an even whole number. So you would start taking 2's away from it, right? So 2, 4, 6, 8. So if you started with, there were 17 sign changes, then there were either 17 positive reals or 15, and then take 2 more away, 13, take 2 more away, 11, right? So you basically just take 2, but we're never going to have something that's 17, right? We're going to have like 5 at the most, and then it's going to be either 5, 3, or 1. In this case, we had 3 sign changes, so it's either going to be 3 or 1. And then negative real zeros is the exact same thing, only first you have to change the function by plugging in negative x, which obviously changes some of the signs. So if we go back to our original function here, actually this is a different one, but if we look at this example, and if we now plug in a negative x to the sixth, right, still becomes positive. So that stays 3x to the sixth, but the power of 5 makes this negative, power of 3 makes this one negative, power of 1 makes that one negative, negative, right, becomes positive, and of course the constant doesn't change at all. So if we did Descartes on this one, we would see that just for the positive roots using the standard one, we go positive, positive, positive. They all stay the same. So it's not till we get to here we change signs here once, and that stays negative. So there's only one positive real zero on this one, and then when we plug in -1, we get one change, stays negative. The second change, right, then goes back negative. So we have either 3 or 1 for that one, right? So that tells us that we either have 3 or 1 negatives, and we only have 1 positive. So that means we either have 2 total or 4 total zeros, right? Remember, these are real zeros. It doesn't count imaginaries. All right. Finding the upper and lower bounds of what our zeros could be also can be helpful, because instead of looking at 20 different possible zeros, once we find upper and lower bounds, we can kind of eliminate some of our possibilities. And so something is a lower bound and something is an upper bound if we know that the real zero is in between those numbers. Now, we can find upper and lower bounds with this simple theorem. Some of this stuff seems kind of complicated, and these are really only time-saving devices. So if any of this is confusing to you, I just say skip it, forget it. It's not worth your time. Just when you do the normal stuff, which is pretty easy, when you do the very beginning rules and you list out your possible zeros, just jump in and start dividing. Don't even worry about Descartes' rule of signs, because who cares how many possible ones there are? Just start finding them, right? Who cares about upper and lower bounds? Because again, just start finding them. So if you want to save some time, learn how to do these. It's really not necessary, and it's really not worth your energy if it's frustrating you. So here's an example of looking at upper and lower, right? And it's all about what happens when you do synthetic division. So again, if you're not, really good at synthetic division, then this is not going to be helpful for you. Okay? But I'm just clicking through the slides for those of you that actually want to follow along with this idea of upper and lower bounds. Okay? Again, not that important. All right. Lastly, always look to technology to help you with these things too, right? You can use graphing devices to find zeros of polynomials. Here's an example. We can graph it. We can use the upper and lower bound thing, but why would you when you can just go straight to graphing it and use the device to find those zeros? All right. So if you have technology, go ahead and use it. If you're not allowed to in the class, that you're taking, then I suggest just using these simple 3 steps and ignoring Descartes' rule of signs and the upper and lower bound theorem, because it's really not going to help you much. You're better off just jumping in and start checking some of your possible zeros. Start with the easiest ones, avoid the fractions until the end. And once you get it down to a quadratic, use the quadratic formula or factor.